Welcome to Circuitvalley. I'm Gaurav. Today I'm going to show you how you can make custom video processing pipeline on a Zynq Ultrascale FPGA, control a camera, stream video from a camera, and get the images of the camera into FPGA. And this very unique video, I'm also going to show you how you can make a Linux V4L2 pipeline. There are not many documentations available how you can make V4L2 pipeline. So for this particular project, we'll be using my Ultrascale Plus ZC102 FPGA board along with this custom board of mine, MIPI CSI to FMC adapter. It looks something like this. Had a FMC connector on the back, LPC FMC connector, and on the front it allows you to connect up to 4 cameras. It fits almost all of the Xilinx Ultrascale Plus FPGA boards. Right now I'm testing it with the Raspberry Pi camera. It can connect to 2-lane and both 4-lane Raspberry Pi cameras. This little FPC adapter you see, it allows you to connect up to 4 cameras to the board, and all 4 cameras can be 2 lanes or the 4 lanes. Right now you can see I have a standard IMX477 Raspberry Pi HQ camera connected to it in a 2-lane configuration. This is adapter cable, standard Raspberry Pi adapter cable, nothing special. You can connect Raspberry Pi cameras or any other camera from other manufacturer which supports standard 2-lane or 4-lane MIPI configuration. You can connect up to the 4 boards to the camera. On ZC102 they both are HPC connectors. These both are LPC, both are compatible. So you can plug these adapters to any Xilinx Ultrascale Plus FPGA board and have at least 4 if you have 1 connector, or at max 8 of the cameras connected at the same time. So this allows you to rapidly prototype and verify your video processing pipeline and get back to your production very easily. More details about this board is available on my website. This tiny board is very nice, high quality, 8-layer board, very well made. All the impedance control traces, maybe you can see in this example, maybe you can see in this other board. These are very appropriately routed. Impedance matches has been taken care. On the bottom side you have EEPROM and some control logic and level conversion for various stuffs, because this camera has reset and other pins which need to be controlled from a 1.2 volt voltage level. So there I have a voltage level converter for that. So let's get started. Connection is nothing special. Same normal cable. You don't have to configure anything or touch anything else. EEPROM is already pre-configured. So we'll move to now VITA, and I'll show you there how easily you can configure this stuff. So right in front of you I got my ZC102 board and the MIPI pipeline all set up, and I'll walk you through the components, what is connected where and how I have connected and why. So this how you can get a basic guideline that how can you set up a video processing pipeline on your own system. Following this information, you can do it with any Xilinx FPGA which is supported by VITA, of course, because there are Xilinx FPGA which are not supported by VITAs, they are old ones. So let's get started. So on the left side you have this MIPI input connector, that's where our camera connects, and there I have connected the MIPI RxCA subsystem. This MIPI RxCA subsystem contains the MIPI PHY and contains few other components to control the PHY, and also contains the video format bridge. So this MIPI PHY receives the data from the camera, converted into a normal parallel video output bus. And right now you can see I have configured this to RAW12 because my IMX477 supports RAW12, configured to 2 lanes. This setting is necessary so that the tool knows how fast these lines are going to be driven and what will be the clock rate. If you drive it, maybe if you write it here 100 megabit per second and you try to drive the FPGA to be 800, then tool cannot guarantee that it will perform as correctly. So it's necessary to tell the tool, if you run it at 700 it will not complain, if you run it maybe 900 it may complain, but most likely not. So I'll let it default because that's my setting. And this VFB video format bridge, if you do not have a if you do not select the video format bridge, it will give you raw video pixels, and that you do not want because the rest of the IPs do not support that. Otherwise you have to convert this video output to your custom format or something like that. Generally you would want, if you want to deal with the Xilinx IPs. So right now we are okay with it, and we allow the register interface because we'll be using V4L2 driver directly from the Linux. We will not be writing driver on our own, so we will let it be selected. And line buffer depth, this is very important. It consumes first of all buffer. This particular camera sensor is capable of 12 megapixels, so minimum what you need is around 8000 or 4000. You can get away with 4096 because it streams 4028 pixels in a line. So I have selected to maximum because it's a big FPGA and I do not have anything else to select. or anything else to consume the bus. This is very important, pixel per clock. This tells you this video output pixels, how many pixels are per clock, and right now you can see it's outputting like 15 bits. So because we have selected, it's outputting 16-bit because we have selected raw 12 there. If we select raw 8, then it will be outputting 8-bit. 10, it will be still outputting 16-bit because it need to be 1 or 2 or 3 bytes, multiple of bytes. So we have selected 1 pixel per clock and T user is enabled. So we do not necessarily need to enable the CRC. You can enable CRC if you're really concerned about it, and it will automatically enable the active lanes. So I'll let it be, and from there, whatever the data get received, so from there, this is the video input configuration of the IP. Few things are important with this IP. This TPHY clock 200 meg. It need to be 200 meg. It cannot be any other frequency. The video CLK as you see here, it can be different than 200 meg. This is the clock for this particular interface. There is one more clock, light ACLK. This is the clock for this particular interface. This is light. This is the axis interface. This is the XE interface which goes to the Linux system or to the Ultrascale Plus PS part, from where it gets controlled. This IP is getting from where the IP is getting controlled. This is the clock of this guy. TPHY, this is the clock of front end. It's need this 200 megahertz to properly receive the data. It need to be 200 megahertz. And you need to make sure that it is 200 megahertz. If it is anything different, you will see the IP misbehaving and you will not know the reason. This video CLK, as I said, interface clock for the data output, it is 200. It can be anything else. Right now, all the clocks are 200 megahertz. I have a reason why all the clocks are 200 megahertz, because DMOSIAC IP only has one clock, and it's basically necessary to keep them all at the same clock. So the reset pin is also driven by a specific mechanism through GPIOs, and then I'll show you in a second. But right now we'll follow the video path. So from there, video goes into a DMOSIAC, and this will just do as the name say, DMOSIAC. It will take the raw 12-bit values from the sensor and convert them to RGB. And this RGB conversion will go to this frame buffer writer. This is the DMA for the Zynq Ultrascale Plus FPGA, and it will take the RGB value and put into the Zynq Ultrascale Plus. DMOSIAC does not have much setting. It only have like how many pixels per clock, what is the maximum width, maximum height, and stuff like that. It is also controlled, the reset is also controlled by a specific GPIO, because these IP under the V4L2 system, they need very specific direct reset control of the reset pins, and the IP expect that you drive a pin or a GPIO or something like that directly to them. That's why they expect you to connect them to a GPIO. So all these reset lines you see, they are connected by a access GPIO driver. You need a GPIO controller because there is no direct GPIO available on the Xilinx Ultrascale Plus, and it is mandatory almost. You cannot get away by driving them with a reset pin or something like that. I mean, you can get away, but then you need to do a lot of hacking on the drivers and everything else, but that's not completely necessary. And there are two interrupts available, one from the RX subsystem and one from the frame buffer writer. This is the DMA. DMA of course needs interrupt, and this guy also has an interrupt to notify the V4L2 drivers. So that's it actually. This is your video pipeline. The data gets received here, get DMOSIAC, converted into RGB by DMOSIAC, get written into the DDR memory of the Zynq FPGA, and then data can be accessed, and you have your video pipeline. What is lot of missing in this video pipeline? This is the bare minimum what you need. What is missing? Color space conversion. If you need some other pixel format other than RGB, that is missing. If you need to do something, for example scaling or test pattern generation or color correction, or many things you can do with different IPs in Xilinx, everything is missing because I don't need it right now. I just wanted to verify if my boards work. So that's what we have right now. This little IP is a reset controller. It's nothing special. It's inherent. It's when you try to drive different IPs from there. So all these IPs, they have been connected through access bus, and all of them get controlled from the V4L2 system. These two things, for example, this has a V4L2 driver, this has a V4L2 driver, and video pipeline controls this guy along with these guys as well. And there is a V4L2 driver for the camera sensor as well, which is not shown of course because it's a hardware part. And of course you need I2C to control the camera as well. So this is the I2C component. It's also got directly written from or directly driven from the Axis bus. This gets also controlled directly by Linux, and there is no hack or anything else. Direct Linux driver for Axis GPIO and Axis I2C exists from the Xilinx, and we use them. For camera enabling, I just constantly driven the camera enable from high, and the clock, this HC102 has a dedicated clock pin, so I'm using that clock pin as an input, and the clocking wizard generates a 200 megahertz clocks using a PLL. So that's it. That is actually all what you have here. And for the DMA ports, this guy connects to the high performance DMA, and the slave port, because it's the master, it generates a transaction and writes to the DR memories. So that's it for the pipeline. And now I'll show you in the Linux how does it behave in the Linux. One more important thing I will show you is that in the Linux, if you're trying to get things working under Linux, you need to get your device tree correct. There's all these components, how they're connected, what are their clocks, how the camera is connected, how these XC GPIO and an XC I2C behave with the camera and control these reset pins. Everything need to be defined. For the sake of simplicity, I have decided to make a device tree overlay. Maybe I'll show you the device tree overlay right now. This is the device tree overlay, and you can see that overlay of course specify the bit stream which will get loaded, and there is a definition of clock for the camera, and the definition of clock, the primary 200 megahertz clock, which is a fixed clock. And now from start, this is what you have. This is the primary Axis component, or this is the primary CSI component. We have defined its address, whatever we was assigned for Axis bus. We have defined all number of active lanes and everything else, and pixel per clock is 1. And the primary thing which you need to take really attention is to these ports. So first port you see here, it is connected to sensor out. So the first ever component in this pipeline is a sensor out. Let's find out the sensor. It must be with I2C. This is the sensor out. Okay, the I2C bus driver, same clock, 200 megahertz and everything else. I2C interrupt is also there, and register address is defined. We have defined all the power supply for the sensor, and I have also defined the I2C address of the sensor. And this is the first endpoint of the video processing pipeline. This is the first input which generates from 2 lanes, primary data, and the link rate is also specified there. I'm running at lower one than what my bit stream was generated for, so it's perfectly fine. So from here, see remote endpoints, CSSI in, and this CSSI in is exactly our primary reception. Here CSSI in, it receives the data from sensor out, and then it does whatever it does with the MIPI data and gives us output of raw form. And this is the pixel format defined 2p. This is the 12-bit pixel, and from there this endpoint connects to DMOD in. This endpoint connection is mandatory. Without that, the Linux will know. Without this, Linux will not know where what connects it, how the pipeline is behaving. So here are the DMOD jack, and we got the same stuff. Clocks is defined, GPIO is defined. These are the reset GPIO from the XC GPIO bus. This is what I was talking about. If you do not define this reset GPIO, you will not be able to instantiate the V4L driver or the Linux driver for the module. So the first sync port connects to the camera handle or connects to the MIPI IRX. So this comes from CSSI receiver, and from here the source port. This port is is the 12-bit RGB value, and by this time it is already converted. So on this port you have RGB, and of course it goes to the video capturing pipeline. And the last component, which is not shown on the on the Vivado bit stream, is this Xilinx video driver. This is absolutely mandatory. Without this, you will not be able to see the div/media or V4L2 devices. This is what instantiate the video pipeline, and this is our frame buffer writer / DMA driver, and this guy uses its DMA. You see it is being referenced here. So they both connect to in such a way that everything is controlled, and these are the pixel format right now I have enabled to support. So it's mandatory. Whatever the pixel format you allow here, these are the only pixel format Linux will recognize. And if you see the error, kind of that 4cc error, which is not supported by that, or video format error, they are caused by that you do not have appropriate value here, or you do not have the appropriate value selected in the bit stream. So this also has reset. It also has, of course, interrupt, primary interrupt control. max height, max width. This is also very important. You need to supply the correct width and dimensions. And actually that's it. You have access GPIO driver, and I have experimented with VDMA and everything else, so you got these things all commented. And if you really need, you can also have the color space conversion. So this kind of color space conversion IP is also instantiated, but it's not called because it's commented. So that's it, 5-6 components you need, and you have the device tree available to you. Now we will boot into Linux. So I'll show you, maybe I'll just show you the log. So this is the log from the last terminal session. And you can see that when the FPGA get loaded, I have instantiated the loading of the bitstream and loading of the device tree using FPGA util. This is the way you load bitstream. This is one of the way you load bitstream on the Xilinx Ultrascale Plus FPGA. And as soon as I did it, it started to load stuff. And here you can see a few messages. Frame buffer deferred probe because of reset GPIO and everything else. This is telling that reset GPIO is not loaded, so I'll not load right now. After that, DMOSIA get loaded, maybe the GPIO driver get loaded by the time, and you can see that Xilinx frame buffer driver later on came and tried to load again and loaded in the device to memory configuration. Of course, the device to memory configuration, you can see the driver IMX477. Also find the IMX, it's a custom driver I have written for this particular platform. There is no public driver available directly for Xilinx, but you can take the Raspberry Pi's driver or driver from somebody else and take a reference from there and make your own custom V4L2 driver. That's not hard. And you can see here frame buffer engine is probed, and the end you can see the driver also found the IMX477, and Xilinx PCAP pipeline also registered the device. So after you did this, then pipeline is of course completely registers. And now I'll show you how the pipeline looks actually. Maybe I'll go down. This is how pipeline looks. So you have the sensor completely in the second number, okay, on the entity number 5, you have the sensor IMX477. This is the V4L2 device. It's provided stream, whatever you have configured. You can configure this resolution here. Not all the resolution are configurable. Whatever you have driver is supported. Right now only 2. Right now my current custom driver only have 2 versions supported, or 2 resolutions supported, 40563040 or 2028 into 1080. These are the 2 primary resolution which I have supported right now. One pad is for configuration, one pad is primarily streaming. This is the pad from where you stream. So you can see 2 pads found, 1 link found, and this pad is connected to CSI to RXS. This thing you need to verify that you are correctly connected. So from there it comes here, and they both are resolution are same. This you also need to make sure. Whole pipeline need to have same resolution. Otherwise you will get some kind of broken pipeline error 32 or something like that, if you do not have the same resolution and everything else. And from here, this is the CSI, and from there it connects to DMOSIAC. Where is DMOSIAC? I can't find it here. Down there is the DMOSIAC, and from DMOSIAC it connects to video capture pipeline. And video capture pipeline shows you that what do you call it? Here at the end, it connects to device node div/video 0, and this is the device node video 0 where you can connect everything what you want. And generally this video, video setup, you can find div/media 0, and all your V4L2 devices, they will be listed under div or sys class interface or sysbus interfaces. And you need to do a little bit more, and you need to configure these buses as well. So I'll show you the configuration script as well. And this is the kind of configuration script it looks, because you need to tell everybody what resolution and what pixel format you are streaming and doing whatever you are doing. So first of all, I configured my sensor to stream into the correct resolution, 1920. First of all, I configured my, even if you say 1920 and 1080 here, you see that I made a mistake, didn't type, but still the resolution bit camera will automatically take the nearest resolution, and it is 2028 by 1080, and everybody will be set to the same resolution. This is for DMOSIAC, this is for CSI to RX. If you have color space conversion, then you can do this as well, the RGB input and YUV output. This is to set the different, different ports. And at the end, you need to select the V4L2 control and set them to the RGB 888. This RGB3 is RGB 888. This is also something which get defined by the device tree, which are the pixel format supported and everything else. So After you've done that, you can use this tool provided by Xilinx. I don't think it's directly from Xilinx, but it's an open source tool. And you can open your device. This you can see camera device is open, captured, started and everything else. And it should look something like this. And you should have number of frames captured by the time, and you will have few frames listed. And if you look at their sizes of course need to be correct as well. And if you look at their sizes also need to be correct as well. Actually, you can see the 3 frame buffers have been captured and 6.3 megabyte has been captured. And these frames, these are not your what do you call them, JPEG or anything else. These are raw byte data, and you will need a specific tool. Previously there was a website available called rawpixels.net. And you can easily view with such website. There are other websites available nowadays. I'll show you in a minute how you can load this stuff to a website, and there you can see what is the content of this particular file. So this is a website called rawpixel viewer or something like that. Previously there was a website called rawpixel.net. I don't know what happened to it, but it appears to be the mirror of it or something like that, or offers the same functionality. You can use MATLAB, or you can even use Python, or many other ways to view those raw files. But I found it very convenient that you can choose your file and do whatever with it. Now I'm at the root, and let's go to the root and VITA. Right now the resolution is not appropriately set. You can see 500 by 12 by 512, and we were expecting 2028, and it's still not right, and 1080. Okay, so you still have really bad looking image. That's because we have the format wrong. And yeah, this is our image. This is what we captured, and this is what we got. So pretty decent quality image. Colors are way off because I don't have any color correction, and you can see that it's RGBA. And if you got something like that, so you can choose all the different formats. I did not know which one is correct, but we'll find out. That's not a big trouble. You can always correct these things. This is not a big trouble at all. And so this appears to be red enough. I would say that it has a bluish hue. This is generally corrected by the ISP pipeline. We can correct it as well. Not a big deal. So I guess that's it for this video. And you can see it's very easy to set up your video processing pipeline on Xilinx, or as well as in the Linux. And in the Linux, primarily thing you need to worry about is the device tree. And the drivers are all of them present, and everything else. You need to set the resolutions appropriately, configure the pipeline appropriately, and then it works. There's not much to it. So that's it for video. You can visit my website www.circuitvalley.com.